Okay, let's go through an example. We will see the fundamental theorem of line integrals at play, but we'll also, just like we did, take the problem in a more traditional sense as well. So let's consider the following vector field. So the vector field is capital F arrow. We could write the of x comma y. I'll just skip writing it this time. Sometimes we'll write it, sometimes we won't write it. Equals angle bracket y comma x. Okay, so there's a vector field defined, and let's capital C be the following. We'll draw a picture of the region we'd like to write our to apply our integral over. So it's actually going to be, in this example, how about there's one right there. We start there, and we end up right here. Okay, so this is part of a circle. Sorry if the picture isn't that clear. Let's draw it a little bigger. Make sure that it's clear. Okay, so let's just put one here where it will be a little easier to draw. That the picture is really more circular. We'll stop there. And so the direction of travel is going to matter. And this angle here is going to be 45 degrees. Okay, so then let's do two things. Part A, let's compute the integral over C of the vector field f dot dr by setting up a dt integral. So we'll do the traditional thing for this. And then part B, let's then compute, same problem, integral over C of vector field f dot dr, but we'll do this using the fundamental theorem of line integrals. And in order to do it this way, we're going to need to first find what function lowercase f of x comma y has angle bracket y comma x angle bracket as its gradient, as the gradient. So let's just do part A first. I know that part B is a little more intriguing right now. So actually let's just work out this first. So in part A we're going to need to look at how C is parameterized. C is parameterized by, well, look, it's part of a unit circle, right? So not too much work here. R of t. So writing this as a vector function, we'll have angle bracket cosine of t, comma sine of t, and t is going to go between 0 and pi over 4. Okay, and then let's compose the vector field with the vector function that we're using for the parameterization. So look at how nice it is. It's angle bracket y, so okay, angle bracket y gets replaced with sine of t, comma, and then we have x here, and x gets replaced with cosine of t. So this is how the contents of r of t gets fed into capital F. And then then we also will need r prime of t. So let's go ahead and compute derivative of each component. We'll have here negative sine of t, and we'll have here cosine of t. All right, so then computing the traditional way, setting up a dt integral. So the integral over c of f arrow dot dr. Okay, this is equal to, well, integral t values going from 0 to pi over 4. And then we've got this times, so we do this dot product, yeah? So we've got sine of t times negative sine of t. And then we have cosine of t times cosine of t. In fact, just to make the order nice, I'm going to write cosine squared t minus sine squared t. And then dt. Okay, so then we'll spare some details, but just comment that there's actually a trig identity that would be helpful for this. So, well, not really spare details. We'll just say there's a trig identity. Okay, integral 0 to pi over 4 of cosine of 2t dt. And then if you applied a u substitution, we'll still write this as a definite integral, but that substitution is going to turn this into integral 0 to pi over 2 of 1/2 cosine of u du, and this is in the end going to equal the number 1/2. So there are still some steps that are skipped here, but hopefully enough steps that you can fill in the details. So that integral can be done completely, and so we're doing it. We're doing it in part because we're going to do the problem again, part B, and we just want to see that the final answer is going to be the same number. So in part B, we're asking ourselves, and this is kind of funky, we're looking for a function, lowercase f of x comma y. What would it be so that in the end, the gradient of this is going to be equal to yx. Now don't overthink this. The question maybe isn't so easy. It feels like you're anti-differentiating simultaneously in x and y. That's what makes it a little challenging, right? But think about it. Whatever we place here, when you partially differentiate with respect to x, you need to get y. And when you partially differentiate this, again, the same thing, with respect to y, you end up with x instead. So just take a moment, think about it. If you can't come up with it, that's okay. Let's just reveal it. We will have a more systematic way to compute these in the future. But let's just, this time, because it's so small, f of x comma y equals xy. X times y. Think about it. Take x times y, differentiate it with respect to x, and you get y. Differentiate it with respect to y, and you get x. Right? So I know this is a little strange. We will have a more systematic way to deal with this in a moment. But let's just now go ahead and compute the integral over C of the vector field dot dr. We're getting lucky that we have, in this example, it's not just any old vector field. It happened to be a gradient field, right? Or we found this lowercase f, which goes by the fancy name of a potential function. And so applying the fundamental theorem of line integrals, we'll have f of vector r of the larger t value, pi over 4, minus f of vector r of the smaller t value, which was 0. We can just read those off of the integral right there. Now we just need to compute, and we'll have here f of, well, let's see, plugging in pi over 4 into this right there, so cosine of pi over 4, comma sine of pi over 4. Well, both of those will be root 2 over 2. Yeah, so we'll have root 2 over 2, comma root 2 over 2, minus f of, and then what point do we have? So r of 0. So go back here, plug in 0 for t, cosine of 0, comma sine of 0. That would be 1, comma 0. Right? Cosine of 0 is 1. Okay, and then we apply f to this input. Where's f? Oh yeah, it's over here. X times y. So we'll have root 2 over 2 times root 2 over 2 minus, and then f of 1 comma 0. Still, again, little f is multiplying the two input variables, so 1 times 0. And so we'll have here, let's see, root 2 times root 2 is 2, over 2 times 2 is 4, minus 0, we won't write that, so 2 over 4, we end up with 1/2, which is the same number here.